Hi, everyone. Uh, so I asked in the chat whether there's anyone actually connected to the live stream, and the YouTube video was kind of buggy, and it does look like there are some people. So let's just start. Today, I just wanted to do a conservation of momentum problem. And next class, I'll do some rotational motion problems, and that'll be sufficient, I think, for the final. Okay, and the final, the third test. Okay, and the format is the same as the previous test format. So let's just jump right in. Uh, I don't think there's much more to really tell you in terms of the logistics of the final test. I'll have more details on Wednesday. I can say this: it's 32 questions long. Okay, so it's a little bit longer than your previous ones, but it's the same. It takes about the same amount of time. Okay, so let's start off. This is a conservation momentum problem. I just realized that actually there's another question that I can ask here at the end. That's how much energy is released, but I'll add a section F when we get there. So momentum, conservation of momentum. Usually it's when things collide, okay, whether in 1D or in 2D, but it could also be when things explode, okay. Momentum is conserved throughout any kind of dynamical situation. And so here I decided to do another one of these examples where I have something blowing apart, and I have a 20-kilogram bomb, and it blows apart into three pieces, okay. I tell you two of the pieces, and I ask you questions about the third piece, and all the information about the third piece has to be determined from the other two pieces because momentum is conserved. Okay, so let's look at it. So we have a 20-kilogram bomb. It blows up into three pieces. There's a 5-kilogram that travels along the plus x-axis. I'll draw a picture in a minute. Okay, and a 7-kilogram that travels along the negative x-axis, not the positive x-axis. Oh, sorry, not the negative y-axis, not the positive y-axis. Okay, again, I'll draw a picture. What I mean by that, but I think it's pretty clear. Okay, what that means, and then I ask a series of questions here. Okay, let's draw a picture. Okay, and then of course there's a third piece. Okay, so let's draw a picture and let's take a look at what's going on. Okay, so initially we have the 20-kilogram in the middle here, and I guess I could draw that in red. Okay, here it is. Okay, so it's ready to blow up, and one piece, 5 kilograms, travels along the plus x-axis. Let me do that in blue. So here's a 5 kilogram. So the red is like the before picture, and the blue is the after. So there's a 5 kilogram right there. And then there's a 7 kilogram, and the 7 kilogram travels along the negative y-axis. Okay, so that means it's traveling down this way, like that. Okay, I think that's pretty clear from the language. Okay, that's the 7 kilogram, like that. And where do you think the third piece is going to go? Well, if you just use your intuition, just think about it. If you've got a piece traveling along the plus x-axis and a piece traveling along the minus y-axis, you kind of have to balance that. So, because you've got some stuff traveling in the positive x, you're going to need something traveling in the negative x. And because you've got some matter traveling in the negative y, you're going to have something in the positive y. So that third piece has to have both a negative x and a positive y. So it has to be something which is up this way, like that. Okay, so that's just intuitive, but your intuition is usually pretty good when it comes to momentum. So we know that whatever the answer is going to be, it's going to be in that direction there. Okay, so the first question asked, let's switch back here. The first question is actually super trivial. It's like, what size is the remaining piece? And the only reason I asked that question is to just reaffirm that this is going to be that this is a conservation law, and it's that conservation of matter, conservation of mass is its own conservation law. Okay, and so in addition to conservation of energy, conservation of momentum, there's also conservation of matter. And so whatever that other piece is, whatever that m is, plus the 5 kilogram plus the 7 kilogram, that's got to equal 20 kilograms. Okay, that's what we mean by conservation law. We have 20 kilograms to start with, and whatever we have afterwards has to also be 20 kilograms. And so that third piece, I guess we can call it M3, that third piece M3 has got to equal 20 minus 12, which is 8 kilograms. Okay, so that answers that one. Trivial, but again, I just added that to emphasize that, there are more conservation laws than just conservation of energy, conservation of momentum. Okay, so the next question I ask is, what is the x component of the velocity? So in the picture I just drew, I said, there has to be an x component an x component and a y component, and the x component we know is going to turn out negative. Okay, just from intuition. Let's see how that works out. So momentum is conserved, and momentum is a vector. So there's a momentum before in the x direction, and then there's a momentum after in the x direction. Okay, and these two values have to be the same. Now, what's the momentum before in the x direction? Well, that 20 kilogram mass, that's what you have before. That 20 kilogram mass, it's not going anywhere. It's not moving at all. And so its x component of the velocity and the y component of the velocity are both 0. And so its momentum is 0. And the units are kilogram meters per second, like that. Okay? But saying 0 is good enough. Okay? Now, this px here is also going to equal 0. But, before we set that equal to 0, let's think about what contributes to the x component of the momentum. Well, it's going to be m1. Okay, I guess that could be like our 5 kilogram. Let me just say here m1 is 5 kilograms, and m2 here is 7 kilograms, like that. Okay, so it's going to be m1 multiplied by v1, but it's only the x component. Okay, and it's going to be m2 v2, but only the x component, plus m3 v3, only the x component, and this is what we're looking for right there, v3x. Why? Because I'm asking for the x component of the remaining piece. Well, this is the 5 kilogram, there's the 7 kilogram, the remaining piece is m3, and it has some velocity v3x, or its x component is v3x. Okay, so if you just substitute in the numbers, the momentum after and momentum before, x component has to be 0. That's going to equal 5 times v1x. Okay, so what's v1x? Well, if we take a look here, the 5 kilogram is traveling along the x-axis. So we just want the x component. If we take a look at that diagram again, that x component there is all of the velocity. There's no velocity at some angle there. Okay, so the velocity is purely along the x direction. So if we go back over here, the x component of that velocity is the full. Oh, I didn't say what the velocities were. Yeah. Okay, well, I guess I should right now. At, let's say, 15 meters per second. And for this one, at, let's say, 25 meters per second. There we go. So the 5 kilogram is traveling along the plus x-axis at 15. And so its x component is the full 15, like that. All right. Now, m2 is 7 kilograms. Its x component, however, is 0. Why? Well, because it's traveling purely along the negative y direction. So if we take a look at that diagram again, you take a look at that vector there for the 7 kilogram mass, and there's no x component to it at all. Okay, so it's purely along the negative y direction, and so its component along the x direction is 0. All right, so over here, that's going to be 0, like that. All right. Okay, and then finally plus m3, and m3 we decided was 8 kilograms, and we don't know what that value is there. Okay, so basically what this is saying is that the 5 kilogram has purely a 50 meter per second velocity along the x direction, and that has to balance against this one, the 8 kilogram. Why? Because the 7 kilogram isn't contributing at all to the momentum along the x direction. Okay, the 7 kilogram is only contributing along the y direction. All right, so it's just a matter of simplifying this. This is going to be 0 is equal to 75 plus 8 v3x, like that. And so that's going to be negative 75 is equal to 8 v3x, like that. And that tells me that v3x is going to equal, and let me divide this number by 8. It's going to be that. Okay. and the units will be meters per second, like that. And so v3x is along the negative x direction, okay, or along the negative x-axis, like that. All right, now that's just the x component, but that was what we intuitively expected, okay, because if we go back to our diagram here, like this, you take a look at the diagram, and let me do this, I guess, maybe in green here. You can see here that, we're just looking at things that are moving to the left or the right, okay? So the 7 kilogram isn't moving to the left or to the right, it's just moving purely straight down. So this one, it's moving to the right, and therefore it must be balanced by some momentum moving to the left, and that's why we got a negative value, whoops, a negative value right here for the velocity. Okay, so there we go. Uh, there's the velocity, the x component of the velocity. Okay, now the next one is, what is the y component? And for the y component, it's same idea here, like that, but now it's the y component. And remember, without the prime there, py, that's just the y component of the momentum before the explosion, and it's not going anywhere, okay? And so it has neither an x nor a y component. All right, so that means that the the y component here, after the explosion, like this, so it's the exact same formula, but with y's in there, it must also equal 0. Okay, so if we plug in the numbers here, y component of the momentum afterwards, same as before, 0. M1, 5 kilograms. V1y, okay, so what does that ask for? That asks for the y component of the velocity of mass number 1. Okay, go back to the diagram, and if you take a look here at this diagram, let's get rid of the green circles there. Well, I guess I could draw it back again. This 5 kilogram is moving purely along the positive x direction. It has no up or down motion at all, and so it doesn't contribute to the y component. This one, however, does. Okay, we're going to look at that one next, but it's not traveling in the positive y. Instead, it's traveling in the negative y direction. Okay, and so we got to be careful with the sign there. Let's switch back. So the 5 kilogram, no y component to its velocity. The 7 kilogram, it has a y component, but it's traveling 25 in the negative y direction. Okay, so over here we got to put in negative 25. The sign is important because it says what direction you're going in, and there are two possibilities when you're looking at a component. For x, it's either going to be to the right or to the left, in other words, positive or negative. And for the y component, it's either up or down. Okay, and again, that's going to be either positive or negative. And in this case, we need that to be negative because it's going in the downwards direction. Okay, and then plus m3, that's 8. Okay, and we want the y component of the velocity of the remaining piece. That's this guy right there. Okay. Let's get rid of that. Okay, so what's this going to equal? Well, I think you guys know how to do this math, so I'm just going to very quickly do it on my calculator here. And divide by 8. And I get this number right here. Okay. And the units are meters per second, like that. Okay. So is this what we expected? Actually, it is not, because I made a mistake. I made a mistake because I forgot to multiply by negative 1. There we go. That's what we wanted. Okay, so 21.875 rounds off to like 21.9 meters per second, and it's going to be along the positive y direction. And again, it's good to use your intuition and check. So if we look at the diagram here, as I mentioned before, that's got a negative y momentum, and so whatever this vector has here, it's got to have a positive y to balance it. These two have to balance one another. Okay, and so the y component of the remaining piece has to balance against the y component of the 7 kilogram, and that's why that y component has to be positive. Okay, and you'll actually notice, I mean, like, I made a stupid mistake. I used my calculator too quickly, and I forgot to put in a minus sign there. And how did I realize that I made that mistake? Because I just cut and paste the number. Well, I realized I made that mistake from my intuition. And like from my assignment, I usually have the right answer and I go to the right or to the left. Okay. And I'm doing that on purpose because I want to make sure that the difference between right and left, positive, what positive and negative mean, right and left, and so on, or up and down in this case. And so use your intuition just like I did in this particular example. It's an easier example, but the reason I chose this example is because the intuition in it is very clear. Okay, where you have to balance the x components of the momentum, and that tells you that the resultant in our first problem has to come out over here, had to come out negative. Okay, and then we had to also balance in the y direction, and our intuition told us that in that case, this had to be positive. Okay, so that's how you'll avoid making mistakes with right and left and up or down. All right, so let me check if there's any questions in the chat right now. Okay, I don't see any questions. So good. All right, so let's continue. And the next question is, what is the magnitude of the velocity? So these are the two components. And I mean, you've worked with vectors a lot now, and you know that that's not how fast it's going. Neither one of them tells you how fast they're going. They tell you how fast the projections along the axes are moving. Okay, so if you had like some kind of a shadow, here I can just draw it very quickly. I know we did this already when we did 2D kinematics, but if the 8 kilogram is right there, the velocity along the y direction would be, if you take that dotted line there and you just made this kind of a shadow there along the y-axis, a projection as it's called, it would have a velocity along that, and that's what we found. And then it would also have, if you project down to the x-axis like this projection here would have a velocity like that, and this one was v3y, and this one was v3x. Okay, and so neither one of them are really the velocity, which is the blue line. Each individually are the projections along the axes. Okay, so if you want the full velocity, just like what you would measure in a lab, well, what's that going to equal? Well, you need to use Pythagorean theorem. Remember, we're converting from Cartesian to polar, so it's the square root of v3x squared plus v3y squared, like that. Okay, so Pythagorean theorem gives you the magnitude. That's equal to the square root of, and the first number we got is this. The negative sign actually doesn't matter because it's just going to get squared. When we square the negative, it'll go away. Okay, and it's this number right here. I put the positive in there just to emphasize that it was in the positive y direction. We don't really need it. Okay, like that. And that gives us, let me quickly work that out. That works out to this number right here, which I would round off on the test to 23.8 meters per second. Okay, so you could see that this number is always going to be bigger than either of the components. Okay, it's always going to be bigger than either of the components. Okay, so it turns out to be 23.8. Okay, now what's the direction of that velocity? And in the absence of any other information, it's always measured counter angle. I should say it this way: the angle is measured counterclockwise from the positive x-axis. Okay, not from. There we go. Okay, and so how do you do that? Well, you might look at the diagram first and say, oh, it has to be in quadrant 2. Okay, so since this is going to wind up in quadrant 2, we know that this angle here is going to be bigger than 90 and less than 180. Okay, and also in quadrant 2, you've got to do this thing where you add the 180 degrees. Okay, so I know we studied that earlier in the course, but it's good to remind you at this point. Okay, and so the angle theta is going to equal the inverse tangent and usually on a calculator that's done with like a tangent to the -1 like that, of the y component, like that, divided by the x component. All right, like that. Okay, and when you do this, make sure you include the signs there. Okay, now the next thing is plus 180 y. We add 180 because quad 2. Okay, so when it comes to angles, if you're in quadrant 2 and 3, you have no choice. You have to add 180, otherwise you get the wrong answer. If you're in quadrant 4, you can optionally add 360. If you add 360, you're going to get a positive value, and then it's still the positive angle measured from the plus x-axis, but you're going almost all the way around. If you don't add the 360 in quadrant 4, you'll get a negative number, and that's okay. Just interpret that negative as measuring clockwise from the positive x-axis. So technically speaking, in quadrant 4, you don't have to add that 360 degrees. Just remember that if you don't, you're going to get a negative number, and that negative number means measure clockwise, whereas a positive number means measure counterclockwise. Quadrants 2 and 3, you must add 180, otherwise you're on the wrong branch of the inverse tangent. You'll just get the wrong number. Okay, so let's work that out. Tangent to the -1 of the y component. Wow, I can't type. The y component is this positive number right there. Okay, and the x component was this negative number up here, right there. Okay, and plus 180, like that. Okay, let me do that on my calculator, and I can give you that answer. So this should work. Is it going to work? Yeah, it did. Good. It's going to equal 113 degrees. Okay, well, that's got way too many digits, so round it off to 113 degrees. Okay, again, does that make sense? Okay, so we can take a look at the diagram once more, and over here, what this is saying is that this angle in here is 113 degrees. Okay, like that. And yeah, it makes sense, you know. If it were less than 90, it'd be wrong. If it were greater than 180, it would definitely be wrong. Okay, and so it turns out to be 113 degrees, and it kind of makes sense. Okay, and it's actually closer to the y-axis than it is to the negative x-axis. Okay, and that makes sense because this momentum here, due to the 7 kilogram, is bigger than that one, which means that this y component here is bigger than that x component there. Okay, and that means that the vector, even though I kind of drew it at 45 degrees, that vector is really more like that. Whoops, no, more like that. Okay, and yeah, that makes sense. Okay, because it's got to have more along the y direction to compensate for the bigger negative y momentum. Okay, so there we go. There's the problem so far. There's one more thing we should do with this. Okay, and that is energy, right? So I didn't ask that question, but I'll add it right now. F, how much energy is released in this explosion? And is the explosion elastic, super elastic, or inelastic? Inelastic. There we go. All right. So how much energy is released in this explosion? Well, let's start off with the initial energy. The initial energy, and you gotta, for now, just like we don't know about heat yet. Okay, that's next semester. We also don't know about chemical energy. Okay, so if you take a look at that red dot there, that's the 20 kilogram bomb or explosives, ready to blow apart. Okay, it's just sitting there. It's just sitting there. Okay, and it's not moving. and so it has no energy. Okay, now I know that there's energy at the chemical level, but if we don't know about it, if we all we know is what's called mechanical energy, that's the energy of things moving. uh, we just say, oh, it doesn't have any energy initially. Okay, and so the initial energy is 0 joules. Okay, but what's the energy afterwards? Well, the energy afterwards is there are three pieces that are moving, and there's no potential energies in these problems. Okay, all right. So it's 1/2 m1 v1 squared. Okay, so that's the potential energy of the 5 kilogram piece, plus same term again, but now for piece number 2, the 7 kilogram piece, and then whoops, can't cut and paste. Can't cut and paste. There we go. Copy, paste. And then again for the 3 kilogram piece. Okay, so there we go. And then that's going to equal 0.5. That's 5 kilograms. And how fast was that V1? 15. It's 15 and 25. Okay, so that was 15 squared. Okay, so that's the kinetic energy of the 5 kilogram piece afterwards, plus after the explosion, 0.5, 7, and it's traveling at 25 squared. Okay, direction doesn't matter here. Okay, so whether this is traveling along the plus y direction, the negative y direction, or even at an angle. Okay, which is going to be a variation I'm going to do next. Okay, even if it's traveling at an angle, it doesn't matter. Okay, it's just the magnitude is all that matters here. All right, and so it's just 25 squared, the magnitude squared, plus 0.5. That's an 8 kilogram piece. And V3, be careful, it's not the x component, it's not the y component, it's V3, it's the entire magnitude. Okay, and I think you guys have gotten used to my notation. If I say V3x, it means the x component of V3, and V3y means the y component of V3. V3 by itself just means the whole magnitude. Okay, and we have that number. Okay, I'll just use that one with all the extra digits so that we get a more accurate answer. Oops, squared like that. And what's that got to equal? That has got to equal this number right here. Okay, which will equal, rounding it off to 50,016 joules like that, or probably better, like on a test, I'd probably write that as 5.02 kilojoules. Okay, so 5.02 kilojoules, which is still not much at all. This is hardly an explosion. Okay, so like food energies are in the kilojoule range. I don't know how much a chocolate bar is, but I'm going to guess is maybe 100 kilojoules. And this is only 5 kilojoules, so this is not a lot of energy at all. All right. So if you take a look at this, you go, well, the energy after is bigger than the energy before. And when there's more energy after than before, it's like energy appeared from somewhere. Again, it didn't really appear. It came out of the chemical energy that we don't know about yet. But that means that it's super elastic. Okay, so just to remind you what the three possibilities are, it's elastic. If the energy before and after are the same, it's elastic. If the energy after is bigger than before, it's superelastic. And superelastic could almost be synonymous with explosion. Because that's what you mean by an explosion. It means like there's more energy after in the moving pieces than there was before. Okay, and inelastic is the opposite. It means, there was a lot of energy before and then there's less energy after. And you go, well, where did that energy go? That's when it went into heat. Okay, so elastic, no energy comes from heat or chemical energy. No energy comes from chemical energy. No energy is lost to heat. A superelastic, you've got, energy coming from microscopics into the macroscopic. That's like chemical energy being released. And an inelastic collision is when you have energy in the macroscopic going to the microscopics, and that's what friction is. Okay, so pretty easy, and there it is. I just wanted to do, I didn't want to do an extra complicated one. I really wanted to kind of aim at the intuition here. So I hope that helps your intuition. Let's just do one more variation on this. So I said repeat, but this time I'm going to have the 5 kilogram traveling at 75 degrees. And I don't even know if we have to do all of this. Repeat the entire problem. The reason I wanted to do that is because I didn't want to just have things going directly along the x and y axis. I do expect you to be able to resolve vectors, and so that's why I did this one here. Okay, so let's go back to the diagram, and now we're going to put the 5 kilogram at 75 degrees to the plus x-axis, okay? So let me switch back here, and let me start with a new whiteboard, okay, like that. All right, and we have a y, whoops, green here, let's switch to black. I have a y-axis here like this. I have an x-axis here like that. Okay, so this is the plus x here. I don't usually draw negative x, but we can if that helps. This is negative x is going that way. Okay, this is positive y up here, and this is negative y down there. Okay, like on a compass you have north, south, west, and east. It's kind of the same thing here. You could say, well, this is the plus y is up, and then negative y is down, and so on. Okay, plus x is to the right, and negative x is to the left. Okay, so we still have the 20 kilogram here, and we still have, let me just see here, we still have the 5. So I didn't write in the numbers. Let me write in. You don't see what I'm doing, but I want to make sure that I don't forget the 15 and 25 meters per second. Okay, so we still have the 7 kilogram along the negative y-axis at 25. Okay, so here's the 7 kilogram. The blue is after. Okay, so here's a 7 kilogram right after the explosion, and where's it going? It's going this way. All right, and that was 25 meters per second that way. Okay, whoops, that's kilograms like that. Okay, now we had the 5 kilogram here, but this time it's traveling at 75 degrees, which would be up like that. Okay, so that angle in there is 75 degrees. Okay, and that's the 5 kilogram right here. All right, so this one's a little harder for your intuition. Okay, you might still guess that you have to have a negative final velocity. Okay, so this 8 kilogram piece that's going to blow off in some direction, it has to have a negative x. But does it have a positive y or negative y? Okay, component to the velocity afterwards, and that might be a little hard for you to see. Except that if you realize that this is actually going at 15 here meters per second, okay, that the y, even though it's at an angle, this y component here is going to be bigger than that y component there. Okay, and so what that means is that these two here have more of a y like that, which means that the resultant will have to have some positive y component to the velocity. So I don't know the angle, but I do suspect from my intuition that it's going to be heading somewhere like in that direction there, like that. Okay, and this is that 8 kilogram piece. All right, and again, this one is a little easy to see. Okay, that it's got to be have a negative x component. The velocity of the 8 kilogram has to have a negative x component, and that's because the 7 kilogram doesn't have any, and the 5 kilogram has a positive x. It's traveling a little bit in the positive x direction, so that means that the 8 kilogram has to compensate that and has to be traveling in the negative x. Okay, but this one, the 5 kilogram, has a positive y component. Well, I guess let me get rid of. I guess I can't erase it. The 5 kilogram here has a positive y component. The 7 kilogram has a negative, and you're not sure which one will cancel or which one will win out. It's actually the 7 kilogram is bigger. The y component of the 7 kilogram is bigger than the y component of the 5 kilogram. And that means that overall, these two together, the 5 and the 7, tend to have a momentum in the negative y direction. And that means that 8 kilogram will have to compensate with a momentum in the positive y direction. Okay, so that's intuitive. That one was a little harder to see, okay, which is why I did the other one first, because I really wanted to nail your intuition, like really get your intuition focused in on what was going on there. This one's a little harder to see, but let's work it out, and let's see how what we get. Okay, so let's go through those questions again. The size is still 8 8. Part B is what's the x component, okay? So let me just copy and paste this, although the numbers are going to be wrong here, okay? So what's the x component? That is correct, okay? Because the 20 kilogram, the before, is not going anywhere, okay? But this, and this is still correct in form, but now your V1x is not 15, okay? It's not 15. I don't know how to do a not, but it's not going to be 15, okay? The V2x, that's still 0 meters per second, all right? Let's push that down a bit. Why? Why is that still 0? Well, you know, again, looking at the diagram, the 7 kilogram is going purely along the negative y direction, has no contribution to along the x direction, okay? So, you know, if the 7 kilogram, that's you know, mass number 2, if it has no contribution along the x direction, then its x component must be 0, okay? But this one's a little harder to see because what is it? Well, go back to the diagram. The vector's at an angle, 75 degrees. So what we need to do is we need to break it into its x component this way and its y component that way. And you say, okay, so what's v1x, like that? And it's the magnitude, 15, okay, times the cosine, because it's the x component, of 75 degrees, okay? And of course, if the x component is the cosine, the other one has to be the sine. You've done a lot of these, but you know, it's worth repeating. All right, so this one is going to be 15, magnitude of 15 meters per second, cosine of 75 degrees, whoops, 75 degrees, and that's going to equal, it's going to equal this number right here, okay? And that's in meters per second. All right. Now, too many digits, but that's okay. You know, we'll round off at the end. Okay. That one is still 0 for the reasons I just stated, and we want the x component of the velocity of the remaining piece. So that's v3x. That's our unknown. That's what we want to solve. Okay. So now when we go to substitute into this, I guess I can just copy that. Okay, down here. When we go to substitute into that, the x component after of the momentum, 0. M1 is 5. V1x, it's not 15 anymore. Okay, it's only this much, 3.88 and some more digits. Okay, all right, so that's what changed. Okay, M2 is still 7. V2 is still 0. M3 is still 8. V3x is still unknown. Okay, and that means, let me work this out. Divided by 8. Negative V3x is going to equal negative 2.426 blah 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 meters per second. Okay, and it's still along the negative x direction, and that's what we expected, right? I mean, when we were thinking about this intuitively over here, okay, right there, I said it's you know, the resultant is going to have a negative x component to the momentum, okay, and therefore a negative x component to the velocity. All right, what about the y? All right, so that was the other question. Right there. Okay, what about the y component? That's still true. That in form is still true. This is not true because that number now, oops, sorry, this number now is going to be wrong, right? Okay, and of course that number is going to be wrong. Why? Well, because now, I guess we can just copy and paste these, okay? V1y, the y component of V1, is sine. Okay, so 15 sine of 75 degrees. All right, and if we take that, cut and paste, we get that number there. Whoops, put a space in there. Okay, so V1y is going to be 14.4888 and so on. Okay, V2y is still, oh, no, it's not 0. I'm sorry. Haha, almost made a mistake. Let's take a look at the whiteboard again. It's 25 in the negative y direction, so it's actually negative 25. Okay, so over here, this is actually negative 25 meters per second. All right, and v3y, it's still unknown. Okay, and so now when we plug in, I guess I can just copy and paste all this. All right. Momentum y component still 0. Okay, m15 v1y is this number right here. Okay, and 7, m2 is 7, v2y is still negative 25. Okay, m3 is 8, and v3y is unknown. And let me just work that out for you very quickly. So what's that going to equal? You know what? I'm going to do this in another step. I'll show you why in just a second. So what's that going to equal? Plus 8. Okay. Now, why did I do that? You see how this turned out negative? Now, that was the harder of the two intuitions to work out. Okay, let's go back to that diagram. So remember I said that the y component, let me do this maybe in orange here. I remember I said that the y component here of the 7 kilogram was bigger than the y component here of the of that 5 kilogram. Okay, well, because the 7 has more momentum in the negative y direction than the 5 has in the positive y direction, when I add those two together, this one dominates, and you get an overall momentum in the negative y direction. Okay, that's what's going on right here. That's why you get a negative number right there. Okay, so the next thing is when I solve this, of course, that negative has to be balanced by a positive. When I solve this, I'm going to get divide by 8. I'm going to get this number right here. v3y is equal to that meters per second. Okay, so they're different than above, obviously. Okay, so v3x here and v3x here. See, this v3x was negative 9 and some change, and this one is negative 2 and some change. Okay, and the y component, this one up here was plus 21, and this one here is plus 12. So again, it's less. All right. So yeah, the fact that the piece is going off in a different direction, even though they're traveling at the same speed, the fact that they're going off in a different direction means that the compensating momentum from that third piece has to be different. Okay, and it's actually going to change the energy and everything else. Okay, so let me see if there's any questions so far. All right, and let me just do the next part, which was what's the magnitude and direction. Okay, so let me just copy down to here. So what's the magnitude? This formula is still correct. Okay, you still do the, it's still Pythagorean Theorem, square root of v3x squared plus v3y squared. The numbers are different now, though, right? So that number is different and that number is different. And of course, that's all going to be different there. So for the x component, we found, what did we find? We found this. Oh, I could take the negative in there, but again, it doesn't matter when you square it. And the y component was this, and this gives me I have this really nice calculator. I use Linux, Ubuntu Linux, and not Windows, not Mac, and it has a really nice calculator where all I have to do is just cut and paste this and it'll calculate it for me. So that's how I'm able to do it very quickly, because I don't have to retype all the numbers. Okay, anyhow, I digress. So that's going to turn out to be 13 and some change, and that's 13.0 meters per second, rounding off to 3 significant figures. Okay, and so this is old hat, but there we go. Now this, it's still in quadrant 2. All right, and we know that it's in quadrant 2 because the x value is negative and the y value is positive. Okay, so that's still quadrant 2. And that's going to give me the y component here divided by the x component here, like that. plus the 180 degrees. All right, I'll tell you what that is in just a second. Turns out to be 100 degrees, even less, even closer to the 90 degree, because I'd round that off to 100 degrees like that. Okay, so back to the diagram here. Okay, again, I exaggerated here, but if I were to actually measure this angle in here, this angle in there would turn out to be 100 degrees. So last time it was 113, now it's only 100. Okay, and that kind of makes sense. Okay, because you've got more of this compensating um, velocity from the 15, so this angle could be closer to the y-axis. All right, and last one. What is the energy, or how much energy is released? Okay, we know that it's going to be an elastic. Sorry, super elastic, because it's an explosion. Basically, if it's an explosion, it's super elastic. Okay. All right. So energy before, well, no difference from above, right? Still 0 joules. Energy after, same structure to the formula. Where is it here? Oops. Same structure to the formula, but the numbers are different. Okay. Well, not all the numbers. Not all the numbers. Okay. So this is still traveling at 15. The angle doesn't matter. So, back here, now that it's traveling at 75 degrees to the plus x-axis, that doesn't matter. It still has a magnitude of 15, so that didn't change. The 7 kilogram, nothing changed about it. It's 25. So these two here, they still have the same energy. This one is different because it's not that for its magnitude, but that's the magnitude. Okay, and so it turns out that actually in this second situation, there's less energy released. Okay, and that turns out to be or 3.43 kilojoules, like that. Okay, so there we go. That's really the only problem I wanted to do today. Um, it um, I don't know. It was more meant to like really hone your intuition into how to do these momentum problems and make sure that you get the signs right. Um, I've noticed that a lot of the mistakes that are made because of the signs, and so if you use your intuition. Like I showed you. I mean, sometimes it can be tricky. It gets tricky if there's a lot of pieces flying off, or a lot of pieces that are colliding. But if there's only 2 or 3 pieces, usually your intuition is good enough to say, yeah, this thing has to be traveling in a certain direction. Okay, like especially in the very first one. If I go back to the very first one here, let me switch. There we go. Go back to that very first one. Where you had the 5 kilogram along the plus x and the 7 kilogram along the negative y. It's so obvious that the 8 kilogram must be traveling in quadrant 2. Okay, to balance the two. All right. You couldn't have something like this. Let me just draw it down here. One piece going this way, another piece going that way, and then like by some magic, this piece travels that way. I mean, you would say, well, look, if these 3 pieces are blasting off that way, doesn't there have to be something balancing it over here? You kind of just sense that these things all have to balance out. And that's it. That's your intuition kicking in and saying, yeah, it has to balance out. And so there's no way you can have these two and not have something in that direction. Now you may not know exactly how much in that direction, but like whether it's up there or up like there, whether it's closer to the 90 degree or the 180, but it has to be in quadrant 2. Okay, and if you know it has to be in quadrant 2, that tells you that the x component, let's do it in green, the x component must be negative and that the y component must be positive. Okay, and so this way you're not going to make any kind of mistakes with the signs. Okay, I mean, a few people have told me, they said to me, well, I did it right, but I missed the sign. Well, that is, the sign is important. In fact, it's almost critical in these problems because it could have something traveling in just a totally wrong direction. Okay, so just draw a quick little sketch like that. I think it'll help. Okay, I didn't do collisions. We did quite a few collisions before, so I thought I'd do an explosion now, and oh, there it is. Okay, so what else do you need to know on the test in this section? A center of mass, but the center of mass problems are also very easy. I'd be more than happy to do one for you. We're running out of time right now, but if you want one next class, you can ask for it, or on the Google Hangouts. But I think next on Wednesday, on the live stream for Wednesday, what I'm going to do is I'm just going to do one or two problems like this, but for rotational motion, and where I might have to do two if I think about it. Yeah, I'll have to do two, uh, maybe three. Maybe three. I don't know. I'll think about it. It's just because I want to cover all the different topics, okay? And if I can get one problem that covers all of the topics together, then I'll do it in one problem. But basically, there it's all of like dynamic. It's like repeating the whole course all over again, but with rotational motion. So there's rotational kinematics, there's rotational dynamics, rotational energy, and rotational momentum. Okay, or angular momentum as it's properly called. Okay, and so I want to make sure that I get a problem that covers all of those. Okay, or maybe two problems that cover them, and that'll be it. That'll be everything that's on your test on Friday. Okay, I right after this I'm going to make a quick little video. I mentioned this in the email. I'm just going to suggest what changes I might make for next semester, and put that out, and then people can just say, yeah, I like those changes, or no, I don't like those changes, or leave it all it's perfect the way it is. I don't think it's perfect the way it is, but if people say it's perfect, don't change anything, then I won't change anything. But I think I'll work out something. There's a couple of things I think that could have gone better. It's very hard teaching this way. I don't like it. I've said it numerous times to you guys. I just don't like teaching remotely. The feedback isn't perfect. Even when you ask questions, like you're typing into a chat, and it's just too distant. I don't like it. But all right, looks like we may have to continue with that next semester. But there it is. Okay, guys. So I don't see any questions in the chat, and so why don't I just say goodbye, and uh, um, no, I'll either see you in a Google Hangout this evening or tomorrow evening, or else Wednesday. Okay, bye bye.